Okay, in this video I want to look at some more examples of finding the kernel in the range. So I'm going to look at this particular function that goes from R3 to R2. So our domain is R3, our codomain or our outputs are in R2. And we had a formula for the kernel. Ker-t is the set of all vectors v in v such that t of v was equal to the 0 vector. Okay, so that means we're looking at a set of vectors x, y, z, where t of x, y, z is equal to the 0 vector. 0, 0. Wait a second. 0 vector, our outputs have to be in R2, so I guess it'll be 0, 0. Anyway, I'm getting annoyed at looking at this set notation. Let's think about this as an equation we're trying to solve and see if we can come up with some restrictions on what does x, y, and z have to have in order for this to happen. So if I'm looking at just this part as an equation, if t of x, y, z is equal to 0, 0, t of x, y, z left-hand side is x minus y comma 0. And if that's going to be equal to a 0 vector, it's got to be a two-dimensional 0, 0. And so we have a system of equations. Now x minus y has to be 0, and 0 has to be 0. And so really this is saying that x equals y, and otherwise everything goes. Okay, so that means that our kernel can be described as x has to be y can be whatever it wants, z can be whatever it wants. So maybe a better way to write the kernel as a set is a set of all things that look like y, y, z. And then if we wanted to, we could come up with a basis for this set. But this is the kernel. This is all things that when you plug them into this linear transformation, you're going to get 0. And you might want to just double check if you actually take this and plug it into the function, you should get the 0 vector. Okay. We also had a way to describe the range. The range was t of v, set of all t of v's, set of all outputs, where little v is in your starting set. Okay. In this case, this is actually going to be almost too easy. It's going to be confusing. It's so easy, hopefully. So vectors v and v are things that look like x, y, z. And then t of v, the set of possible outputs, t of x, y, z, according to the definition, is things that look like x minus y comma 0. And so if we wanted to, we could rewrite our range as the set of all things that look like x minus y 0, where x, y, and z are real numbers. Notice z isn't even appearing, but sure, it could be a real number. Again, probably if you wanted to, you could find a basis of this. The basis would be, well, just constants comma zeros. So actually we could probably rewrite this as the span of 1 comma 0, since everything in that set is a multiple of 1 comma 0. Same thing here. If we wanted to, we could write this as a span of y's are multiples of 1, 1, 0, and z's are multiples of 0, 0, 1. So the span of 1, 1, 0 and 0, 0, 1 would spit out the same set of vectors described above, because that is exactly how you would write linear combinations of 1, 1, 0 and 0, 0, 1. Okay, I'm going to pause for a second and switch to a new example. Okay, we're going to try and find the kernel and range of a transformation that's actually a matrix transformation. It's defined by a matrix. And let's look at the size of everything for a second. A is 4 by 2, 2 by 4. 2 rows, 4 columns. X, if it's a vector, in order for this to make sense, it would have to be a 4 by 1. And so my output would have to be a 2 by 1. And so the domain, your inputs would have to be 4 by 1 vectors. Your outputs would have to be 2 by 1 vectors. That means that T is a transformation from R4 into R2. So our kernel should be living inside of R4. Our range should be living inside of R2. So let's start off by looking at the kernel. Kernel of T is the set of all vectors V, where T of V is the 0 vector. And again, I'm going to think about this as an equation. When is T of V equal to the 0 vector? T of V would be A times V. And so we're really solving an equation. I realize now I'm switching back and forth between V's and X's, but I guess that's okay. Our output would be a 2D vector. Okay, so solving a matrix equation, we've done this a million times. You'd write the auxiliary, the augmented matrix, 1, 1, 1, 1, 0, 1, 2, 3, 4, 0, and then row reduce. I happen to have that written next to me, and it row reduces to 1, 0, negative 1, negative 2, 0, 1, 2, 3, 0. Okay, so we have leading ones in the first two columns, no leading ones in the next two columns. So that means that these two columns could be whatever they want. The variables v3 and v4 could be whatever they want, but the other two variables are determined. This is going to end up being v2 plus 2s plus 2t is 0, so v2 is minus 2s minus 3t. v1, similarly, we're going to be able to come up with an equation. It's going to end up being s plus 2t. And so our kernel is a set of all vectors v that look like s plus 2t, comma, minus 2s minus 3t, comma, s, comma, t. That's the set of what vectors v would have to look like in order to have t of v be 0. And again, we could find a basis for this if we wanted to just separate the s and the t bits apart. Okay, our range is a set of all outputs. So if v is, instead of using v1, v2, v3, v4 to make my life a little easier, I'm going to use a, b, c, d. Then t of v is going to be 1, 1, 1, 1, 1, 2, 3, 4 times a, b, c, d. And if we multiply this out, we have, let's see, this 1 is going to end up multiplied by a, the 1 is going to end up multiplied by b, and we have something utterly incomprehensible until you split it up into separate coefficients, as though we were trying to find a basis for this. And suddenly it doesn't look so incomprehensible anymore. This is linear combinations of the columns. And so the range of t is actually the column space of A. So I'm realizing I should have made a completely separate video talking about just matrix transformations, but we are where we are. We've determined that the kernel of T, which is also known as the null or null space of T, is also going to be the null space of the corresponding matrix A, if we have a case like this where T of x is equal to AX. The range of T is actually going to be the column space of A, column space of the corresponding matrix. And we've talked about before how you would actually find a column space, which is either take the transpose and row reduce, or row reduce and look at the non-zero columns. So we actually already row reduced the matrix A, and we got leading entries in the first two columns, which means that our first two columns should be a basis for the column space. So the column space is going to be the span of the two columns 1, 1 and 1, 2. So I'm using a theorem from a couple of sections ago when we were talking about row space and column space.